Okay, I'm very happy to have Eugene here to tell us about quiz of the affine category.
All right, thank you so much for inviting me. So I'll talk about a bunch of joint work. So there are two joint papers with Andrei Negut, with most computations kind of relevant for this. There are earlier papers with Paul Wedrich and Matt Hogenkamp and Paul Wedrich together. So like 4 papers in total about this kind of stuff, but I'll explain what's in which paper. And somehow kind of one big goal, so just to keep in mind, is to categorify the skein of the torus. And I'll define what this is, but the main goal actually is to define all the words in this title. What is affine Hecke algebra? What is affine Hecke category? What is the trace? What kind of trace I consider? And how to actually compute with anything like in some kind of concrete ways. So I will go pretty slowly, and please stop me if you have any questions.
What?
I don't know.
I mean, suppose you can do it, then what?
I mean, I don't know.
Sorry, I don't mean to be negative. I'm just asking, suppose you can do it, then what?
I mean, this is supposed. We'll get there. Just that's fine. I want to go slow. Like, we'll see. Okay, so first of all, I want to talk about Hecke algebra. So first of all, there is the usual Hecke algebra. Hn. So I have generators T1 through Tn-1 and relations Ti plus 1. Ti is Ti plus 1. Ti plus 1. Ti Tj is equal to Tj Ti if I and j are apart. And the quadratic relation that Ti, I think I want this is equal to 0. Let's see. Yeah, that's what I want. And so that's some algebra generators and relations. If you don't care about the algebra, you can think about it as some kind of skein algebra. So you can relate it to the braids on n strands, mod skein relation. And skein relation says that if I have a positive crossing minus negative crossing, this would be q minus q inverse times identity. And so the translation from here to here just says that my Ti correspond to the crossing between ith and I plus first strand. And my Ti inverse correspond to inverse crossings, the negative crossings. Then the braid relations are satisfied by this. And then quadratic relation just translates into this skein relation. That's standard. Maybe let me not to explain. This is also maybe Ti minus Ti inverse is just q minus q inverse. And if I have any braid, I can just basically write it as a product of generators, and then this will give me some element here and so forth. And kind of everyone's seen this here, and maybe kind of one thing to keep in mind is that you have a basis given by TW, where W is an Sn. So if I have any permutation in Sn, I write it as a product of simple transpositions and lift it to Ti. So if I write my W kind of Si1, Sik, then Tw just Ti1. Okay. So this is easy, but again, this is kind of picture that I like, that just braids on n strands, mod skein relations. So the next algebra, oh, it doesn't go all the way up. Okay. Is affine Hecke algebra. And you can define it in many different ways, but I want to say it this way. So you have generators T1 through Tn minus 1 and T0. And then I have additional generator omega. And then relations are the same as before. So my indices are understood mod n. And so in particular, there is a braid relation between Tn-1 and T0, and there is a braid relation between T0 and T1, which maybe I don't want to write. If there is additional relation with omega, doesn't matter what it is, but it is omega Ti omega inverse is Ti plus 1. And so if you've seen this kind of things before, you can also think about the Dynkin diagram for affine AN, where you have this kind of 0, 1, 5. At each node, you have this Ti. Each edge corresponds to a braid relation, and then omega kind of rotates this diagram around by 1. Okay, and okay, so this is nice and abstract, but if you like something more concrete, how do you think about this? So this is, again, so has some scaling theory description. So these are now braids in the anodes across some interval, mod scaling relation. So I draw my cylinder like this. And then I choose my endpoints here. And then I can have some braids here, but the braids could also wrap around this hole and go up. So my braids always go, so here I have n of these points. In the output, I have n of these points. And in principle, my braids could go, like they always go up, but they can go around this in positive direction. They can go around this in negative direction. So there are no restrictions. And then locally, I still have that scaling relation. And this perspective gives us a lot of other interesting generators. In particular, useful guys are yi, which are Ti inverse T1 inverse omega Tn minus 1 Ti minus 1. Okay. And so omega kind of rotates the whole thing around this thing, and then yi, it just you rotate I strand around the hole. And in particular, you can check that yj is equal to yjy for all nj. So I have a big commutative subgroup of this kind of loops wrapping around this hole and going around. So for y, I mean, so I fix, so y1 would just like go around this thing and come back. Y2 would go around the first strand. So the first strand is not changed, but then the second would kind of wrap around it and come there, and so on. And again, you can ask lots of different questions here. Yeah, so in particular, you have a basis. There you had a basis for W and Sn. Here, I don't know if you guys care, but you have a basis, sorry, TW, where W would live now in a affine symmetric group. And you know what's a affine symmetric group, that's great. If you don't know, maybe I won't define it. But somehow the most important thing is that Hecke algebra is finite dimensional. So we take all possible braids on n strands. There are infinitely many braids. It's a giant thing, but once I quotient by scaling relation, Hecke algebra is actually finite dimensional, it has dimension n factorial, because you have a basis given by permutations. This thing is certainly infinite dimensional. So dimension is certainly infinite. But you can work with it. And kind of one useful structure which you have for affine braids and you don't have for braids is various actions and multiplications. So you have multiplication when I go from, let's call this affine algebra. So I have multiplication from AHN and AHM to AHM plus n. And how do I build this? I just put one cylinder inside another. So I can say, well, one cylinder, which is very big here. And I have another cylinder. And then I have even smaller cylinder in here. And then I can put somehow endpoints here. And I can put endpoints here. And then, I mean, they don't interact with each other. So I can put endpoints in the center. They can wrap around, like they stay within this medium-sized cylinder. They wrap around this middle hole, but they can do whatever they want. And then these endpoints wrap around this middle cylinder and come back. So you have this, and you can concatenate this, and all these guys from here would commute with guys here. And all the guys from here will commute with the guys there. So that's kind of useful thing to have. And in particular, we can, if I have some generators, I can combine them using this. Maybe I'll put a star here, just indicate that this operation. If you've seen skein algebras, and I'll come back to skein algebras in a second, this is similar to skein multiplication because I put kind of this red braid on the top of the yellow braid. And so this is really kind of skein multiplication. The only difficulty or kind of a feature here is that like we deal with braids, so we need to control what happens on the boundary. And this is not commutative, so I couldn't swap this yellow and red. It's important that yellow are on the inside and red is on the outside. And you can also have an action of AHN. I don't know, let's say HN actually. Let's say HM plus HN. So H plus N, where instead of this, I just fill the hole. So I can say, well, I can this. So I can have my endpoints here. And I can have my endpoints on the outside. And again, this will live in this tube and transform by according to some braid. This would live on this outside cylinder and transform according to some affine braid. And then the result will be a finite braid because there's no hole in the result. And so you have an action of affine Hecke algebra on Hecke algebra, which results into some other Hecke algebra. And you cannot do this with normal Hecke algebras because you need this hole. So you need to have this affine and this fine somehow, right? And then maybe if n is equal to 0, so this is kind of specializes, and n is equal to 0, you have kind of flattening map from AHM to AHM. Yes?
So you have AHI times HN equals to H.
Yep. So again, HM means that I have M red points here, which are allowed to live in this region, but can transform with time. And then I have HN, so they stay in this middle cylinder here. And then altogether, if I just concatenate these braids, kind of just take the union of them, I will have a finite braid in HM plus N. And of course, all my scaling relations are satisfied and everything is fine.
Like TI from the M affine Hecke algebra and TJ from algebra go to something like TI plus J or something.
I mean, there will be like if I have TI like here or here, where? Like here, for example. So like TI here will stay to TI, but TI here will be something like TI plus M, right? So here the generators will be something like, roughly speaking, TI. This will be TI plus N because all of them are shifted like this N strands. So if I think of this crossing on the red strands, like all the yellow would stay the same, right? And so this is really I plus N's crossing there.
Product of the two will be TI plus.
No, the product is the product. It's like TI times TJ plus N. So it's not that the like two crossings don't multiply the crossings. So, yeah, I mean, another kind of good way to think about it in terms of this y's. So yeah, so what happens with T0 is kind of tricky because T0 is tricky. But if you think in terms of y's, I can say, well, so y's here, they wrap around, like I strand here wraps around and goes back to cell. Here, it also goes back to this y is kind of naturally just glue. And then this finite TIs, except for T0, everything is just like very straightforward. Yeah. So you can write all this in generators and relations, but like you can also draw this and just, I'm trying to convince you that it's fine. Okay, more questions about affine Hecke algebra?
And to circle, you allow this, bring the cross, closing the circle.
I'm not closing yet. I will close in a second. Yes. So I will close all this in a second, but right now, like the strands don't cross, nothing crosses. It's just like they, yeah.
So sorry, you know, you could take Hn to be H0 is the hidden solid.
Yeah, exactly. Yeah, that's what I'm saying here. Huh?
Which element is being killed?
I think y1 is killed, but you can also say, like, yeah, one way is to say is like y1 is killed because it wraps around this middle cylinder, and then you just remove the cylinder, and then y1 will be trivial. That's right. So you have this projection, and like, for example, y1 would go to just 1. And I think that's the only thing which happens, and then that's the only relation in this projection. Yeah.
Can you say again what T0 does?
I mean, it's like n strands goes around and like crosses the first one. It's not easy. Maybe you can express it through this, right? So if I have, like, I mean, one way to think about T0 is to say, like, I understand this y's really well, so I can use this relation to understand what omega does. And then if I understand omega, I can like reconstruct my T0. I don't know. It's not an answer. I can draw it, but it's not really helpful. You change them in the first, but then you have to kind of keep track like how they wrap around. Yes. Okay. More questions? We're good. All right. Okay. So these are the algebras. Now let's close up and talk about the traces. So, okay, so if I have an algebra, hey. So the co-center of the algebra, sometimes people call it the trace, sometimes people don't call the trace, is this. This is the co-center. And so this is, again, some generators for x in my algebra. And then the relation is that xy is equal to yx for all x and y, right? So that's what this basically means. How to think about this in our terms. So if I have some kind of braids, so if this is my x, it's an algebra. If I want to impose this relation, I can always think about this like this. So I put x and y next to each other, and then I close up in the puncture play. And then I'm saying, so this thing is actually the same thing as x, y. Because I can take my y, I can slide it around, it goes upside down, and I can slide it around again and it goes here. So this is kind of diagrammatics for this relation. And so the way we should think about this is that with, so again, okay, the trace of the Hecke algebra, this will be now closed brace. No, it's not an algebra. There's no multiplication, right? So you couldn't, like before I could compose x and y, but like now I couldn't do anything. Like, yeah, so there's no multiplication, it's not an algebra. That's a good point. So this is an algebra, this is just a vector space. There is no algebra structure at all. And I can think about this vector space as closed braids. If I start from Hecke algebra, which was like braids here, mod skein relation. So I can close up the braid and then close braid, let's say in punctures. I mean, there are too many annuli here, which is confusing. So maybe let's say puncture plane. Mod skein relation, which is more traditionally is called the skein of the annulus. So this is spawn fly PT or like whatever spawn fly. Okay, so I can pick my favorite braid, like this one, close it up, but I keep my puncture here and I'm not allowed, so my strands are not allowed to cross this puncture. But I can slide things around, and then this would basically give me this relation xy is equal to y. So if you've seen like Markov moves for braids, we allow one Markov move, but not the other. We're not allowed to change the number of strands. We're only allowed to kind of slide things around. So the number of strands is fixed in particular. Like how many times we wrap around this thing is fixed.
So the A, with A, is that a ideal?
Yeah.
No,
So, I think ideal generated by this stuff. I think like two-sided ideal in the algebra generated by this stuff. Sorry, maybe I don't do ideal. No, I just quotient by this relation. Yeah.
but before we by an ideal generated by anything,
Yeah.
then you get algebra. But I think you're saying.
Yeah, we're not quotiented by ideal.
Just quotiented by vectors.
Yeah, that's right. That's right. Yeah, sorry, I'm confused. Yes. We just quotient by vector space, we get a vector space. So yeah, there's no algebra structure.
So the A bracket A, it means the subset.
So this is
space generated
by the differences. Yes.
Oh.
It's like this is literally the span of the differences. Yes. Yeah. Yeah. Okay. All right. Yeah. Okay. And then we can describe this thing. So it's a bit non-trivial, but it's not hard. So it's a theorem of derived. For example, in some form, is that term of Hn actually has a basis of this form. So I have something like this, maybe something like this, maybe some other things like this. So I have n1, n2, 3, so on. And then I close up. Maybe I don't want to close up, but like closure of this thing. Right, so this is one way to think about this is a subword of T1 to Tn minus 1. Okay, so if I draw some picture, this is a braid, right? So this is T1, T2, T3, then T4 is missing, T5, T6, and then T7 is missing, and T9, and so on. And we can also assume that this would be N1 is greater than N2 is greater than 3. Okay? Should I close it up, or is clear what's going on? So I take this braid and just close it in like this. But there are many more braids, so it's not obvious, and somehow it takes some work to prove that like the closures of just these braids generate everything. So if in particular, if I have something like 1 to 1, so this is not in this list of braids, right? Because I have more complicated crossings. But I can slide this crossing around. I get, so this was T1, T2, T1. I slide this last T1 around. I get T1, T1, T2. Maybe I don't want to draw this. Then I use quadratic relation and I simplify. Right? And so I can, in fact, like if I use these things in the annulus, I can always simplify. So I have just like T2 or T1, T2 in this way. And then, yeah, derive for like there are many other proofs of this that you can simplify to these things. And then there is a separate argument why these things are actually independent in the trace. And so the dimension of the trace, so I didn't, yeah, this is the trace of a say this. And so the dimension of the trace of the Hecke algebra is the number of partitions of n. And if you like some other description, and people talk about this, of course. So some other description, if I take direct sum over all n trace of Hn, this is just lambda. So this is the ring of symmetric functions. And somehow, if I look at the trace of given n, this is the symmetric functions of degree n. And there is a way to say like which symmetric function corresponds to this thing and so on. So lots of beautiful story. Let me not talk about that. Okay, questions? Only positive rates. Yeah, I can always, like, if I have negative rates so far, I can just like use chain relations and make it positive, right? So I can always change my negative crossing to positive crossing. And yeah, so only positive rates. And also kind of what I was trying to say is here is that there are a lot of positive rates. Even if we use quadratic relation, there are still n factorial of those. And there are much less of this because you can slide things around and you can control them better. Okay? All right. So what about affine? So, okay. So we kind of understand how to close up finite braids in this way. So let's think what happens if I close up a affine braid in Dynus, and let me try to draw this. So what about trace fine Hecke? Well, I take this picture. And I close it up like this. There is still a hole here. There is kind of an empty cylinder. Maybe I'll fill it in. And then there is a big cylinder around. And so you have a space between kind of the big cylinder, which is empty, and then the solid cylinder, which we're not allowed to cross. And then we have some kind of braid here. So we have n points here, which may be wrapping around somewhere here. I don't know, crossing. And then we close it up like this. And so if you think about this for a second, then my trace AHN is the same thing as the braids, so closed braids in my annulus cross S1, which is the same thing really as 2 torus times whatever interval Monskin relation. And so this is really the same thing as this Hornfly scheme. The torus. So where is the torus? The torus is just the surface of this thing, right? So here I have a cylinder, but like once I close up the cylinder like this, it becomes a torus. And now it's thickened in this direction. So there is some thickness between here and here. And so this, where this orange braid leaves, is a thickened torus. And so, and again, I close up, so there are no even crossing there, and some crossings here, but I can use my skein relations locally here, and I can slide things around as I did before. So this is
Hopefully doesn't enter at all.
A of the Hornfly doesn't enter at all. That's right. Like if you frame things correctly, it will come as some kind of framing thing, but like.
But in particular,
Yeah. It could be SL2, but it's really Hornfly because in SL2 you have more relations. That is the problem somehow. But I mean, it's related. Project. I mean, you can resolve the crossing by like this cap and this thing, and here you can.
framing.
I mean, but like Cup bracket is scaling relation is different from conflict scaling relation.
It's just by the frame effect.
Yeah.
And again, those are.
Yeah, but then you need, like, you have more relations in the, so skein, like conflict skein of T2 is bigger than SL2 skein of T2 because you kill more stuff there. Anyway, but like, what do we know about conflict skein of T2? And like, surprising, like, if we do this like SL2 skein of T2, I think it's like 3-dimensional. I don't know. It's not big.
Absorb the A of the conflict.
Yeah.
You can always do.
Yeah, but like if I have some kind of framing, then yeah, then this would give me A. That's right.
Back to one more, you only allow the phrase that going in one direction.
That's right. Yeah. So this is a bit of a lie. So it's not the full conflict, just only things which go around in one direction. But it's like half of my skein, roughly speaking. The same thing there, actually.
I mean, it is your only.
Okay. So what do we know about this? So that's old stuff. Derived is like late 80s, I think. And it's not hard. This is surprisingly much more recent result of Morton Samuelson. Which I want to advertise in every talk, I think, is that if you take the direct sum of Roland, the trace of AHN, this is actually called elliptical algebra. At U is equal to T inverse S, how you normalize this thing. And so what does it mean in practice? In practice, this means that I have generators, which would be PMN. And PMN is what? So this is the trace of the following thing. Try to get it correctly. Omega M T1 through Tt minus 1, where D is GCD sum n, I think. So the algebra structure comes from that. So from that. Yeah, so with respect to, that's good point. So with respect to HM, kind of HM plus n. And we have generators. So if it's non-coprime, you have to be a bit careful. If it's coprime, you should think of just M enters not. So if GCD is 1, EMN, just MN. Not. And so you should think, so what is torus not? You have the surface of the torus. You draw a straight line with slope m over n. So it goes m times around this direction and n times around this direction, as it should be. And it is some picture drawn on the surface of the torus. But like if I look at this carefully, I can kind of put all the crossings in this region, draw it as the closure of some braid. And this braid is just this omega to the m in this case. And then if it's non-coprime, you would have like d different components and you need to glue them by this thing, basically. So there is some technical point, but like you should think of this as really just m n torus not. And now you can ask, what is the basis? And the basis will be important for us. And so the basis will be PM1 and 1, PM2 and 2. 1 second. Where I want M1 over N1 to be less than M2 over N2. And yeah.
Your omega is in where?
Omega, so this lives in AHN. That's a good point. So in AHN, I can draw this affine braid, close it up. It will be n-strand braid. and then this is this. So yeah, I mean, it's not symmetric in M and N in the sense that like this picture is not symmetric. We have N strands going this way and kind of M rotations around this hole. Yeah, and then the point is that, so I'm not writing all the relations between this because that's too much, but you can resolve, so the statement of this theorem in particular is that you can resolve any single closed braid in this solid torus, thickened torus, by the products of these PMNs. And then you can also reorder my PMNs so that the slopes are increasing. So these ratios of M's to N's are increasing. Okay? And you can reorder them using some kind of relations there. And this is a lot, actually. So again, I was saying that affine Hecke algebra is infinite dimensional. What is the size of this thing? How do I even think about this thing? So one way to think about this is I have my point 0, 0. I have my point Mn. And I have a convex path. So this vector will be N1, 1, and 2, and 2. Okay. 1, 4. And so you have a basis here corresponds to convex path from 0, 0 to, let's say, N, where N is the N1 plus R, and M is M1, MR. Okay? And that's already a giant thing. Like M's could be positive and negative, N's must be positive. So maybe let's say, so Mi are actually in Z, and Ni Z positive. And in some sense, that's a complete description. I mean, we still need to write some relations, maybe, but at least I have a basis of this trace as a vector space, which is given by convex path. And that's already like very non-obvious thing if you think about this. That like, and my derived basis over there is actually a special case when all the M's are equal to 0. So if all Mi are equal to 0, get derived basis. Because I'm like all these things are just on one line, and we can reorder them as we want. And so this is just my partitions of M. And like topologically, this match up. So M is equal to 0 means that I like never wrap around this core, and I have actually finite braid. And so this is in perfect agreement. So my Hecke algebra is a subalgebra of affine Hecke algebra. My trace of Hecke algebra is subalgebra of trace of affine, which is embedded like this. Okay. Yes.
What traces have an algebra?
It doesn't.
Called it a Hall algebra.
This algebra, this product structure, because this glues different ends. So this is the structure which I will write in here. Yeah, so if I have affine Hecke, this is very special for affine Hecke, that I can put like one cylinder inside another cylinder. And this is the skein product in the thickened torus. So this is the same thing in the skein product. Okay. And so, yeah. And then there are some relations for this depending on Q, which I don't want to write. But somehow the goal now, like answering Nina's question from the beginning, what's the goal and like why do we care about any of this? So I'm interested in categorifying this theorem in particular. Like we understand pretty well the structure of the Holmfly skein of the torus. We have some generators, we have some relations, we have some bases. Now I will try to explain how to categorify like all these steps. What is categorification of Hecke, affine Hecke? What is the categorification of the trace? And then kind of what do we hope and what can we prove about this kind of statement?
That this will become categorified to all algebra with respect to Richard's development, or
No, not really. Yeah. I mean, there will be some category here, and like like it should be related, like kind of the baby statement is that they should be related to elliptic whole algebra for generic U and T, but like there should be some category, and like I'll try to explain which category it is.
How long are the damages of zero? These are circles, right? Running around the phone.
I mean, these are braids, so I can like braid here. No, because then like precisely that's the previous question. Then I have like if I don't wrap around here, then I have like some finite braid here, right? And so then like finite braids, we don't always simplify to nothing, to identity. We simplify precisely to this derived basis, which was there, where like, I mean, if I have one crossing, I couldn't simplify it. No, not completely, no. I mean, no.
I see.
Like if I have one single crossing, I couldn't. That's where n dependence, yeah. Exactly. Like for SL2, actually, yeah, you can like completely solve because like your crossing will be this minus this kind is swallowed. That's right. So for SL2, you can, and that's why SL2 is so small. But like for SLN in general, it's a bit more subtle. Like you can say, like for SLN, like if I think carefully, I think I can say like what is killed in this quotient, but like, so there is a quotient from this picture to SLN scheme. That again?
Oh, no, it's infinite.
I mean, dimension of this one is infinity. If I don't wrap around, it's partitions of n. So it's still non-trivial, yeah. And this one is like very much infinity because I have this convex path picture. Yes.
But in the case when all NI's are zero, there's no relation, no constraint coming from that monotone.
Yeah, then you're just saying that you can reorder these n's. So if they all have the same slope, you need additional reordering thing, which I didn't say. Yeah, I mean, like basically, I can say like I can reorder two, like so there's some formula which says that the commutator of two of them is some kind of combination of smaller things, roughly speaking. And so I can just choose how I reorder. And like here, I reorder according to the slopes, and then if they have the same slope, I need to further reorder according to kind of answer. Yeah. Okay, so let's talk about verification. And I'm not defining a lot, but I'm just saying, so, and I'm following Katarina's talk from 2 weeks ago. So Hn is categorified by Soergel bimodules. Let's call this as B1. And my Hn is categorified by affine Soergel. Okay, and I really don't want to define either of them. You might have seen Soergel bimodules. If not, don't want to do this. Define this. Affine Soergel bimodules are essentially the same. And here the idea is that like affine symmetric group is still group generated by reflections, and you can define Soergel bimodules for any group generated by reflections. So the definition of all these TIs will be very similar to the normal TIs here. And then there will be one special thing for omega, which is also easy to describe. So let me just say key properties without definitions. Huh? We'll see. Let me just list key properties and we'll see if like this is enough for you. Or I can define this, but it will be like another half an hour. Okay, so what are the key properties? So key properties, so these are graded categories. And my Q corresponds to the grading. Then, and there's a monoidal, that's important. So let's say tensor categories. So my TI correspond to what is called Hecke complexes. All Soergel bimodules. And they satisfy braid relations up to homotopy. And kind of this is all cool, but one technical issue, which I'm not even explaining, I will say what is skein relation. They have skein exact sequences, which is that I have TI, I have canonical map from TI to TI inverse, and I have some complex built out of the identity. And here I have some like xi minus xi plus 1. And so we have exact triangle. Relating TI, TI inverse, and two copies of identity, which you should think of categorification of your skein relation. And kind of the key property is that, of course, K0. So the Grodny group of SBMN is my HN, and the Grodny group of affine SBMN is affine HN.
You know how we get the circle bimodules from the Hilbertine construction that all three categorifies?
I mean,
You don't?
I don't. I mean, maybe Alexei knows. I don't know. He has some ideas.
So it's not some standard stuff. No, no.
I mean, it's not some standard stuff, but it's like the main goal of a Blanco-Ferzanski machine.
Not that it doesn't follow.
I mean, they have a relation between their stuff and affine Soergel bimodal. Like fine is Soergel bimodals, and then you can ask about affine because they have something for affine braid group. And maybe they prove something, I don't remember. Like anyway, that's very far from. It's not that far actually. We'll get to some related questions. Okay, but like this is really just Soergel. So this is much older than like all what we do. So this is resolved by Soergel, who said like if I have any reflection group, we can define the Soergel bimodules. We can run all this machine, and then we have all these nice properties, and this categorifies the corresponding Hecke algebra. So here we only use the fact that, so this is, let me say, this is associated to Sn, and this is associated to Sn fine, and these are groups generated by reflection. These are really Coxy groups. And I want to emphasize that, like, I mean, there are some other kind of more geometric graph theory construction of how to deal with categorification of affine Hecke algebra due to, I don't know, Bezrukavnikov and other people. And like it all uses like much more complicated geometry than this, because you have to use suddenly instead of flags, use affine flags and lots of different things. But here we're saying everything is like really the same. Like there is no big conceptual jump going from Soergel bimodules to affine Soergel bimodules, because this is the same construction. We just have to define what is T0 and what is omega, roughly speaking. So this is, there's no geometry here. Absolutely. There's no geometry, like precisely because we like, there's kind of, this is more or less as hard as this. Like we'll see what's different here, but like conceptually, we just do exactly the same procedure as we do for finite, and like not much changes.
But the TI inverse goes to what? One goes to
1, and this is xi minus xi plus 1. So this is like two-term complex. Maybe let me write it better. This is 1, goes to 1. So there are some variables xi sitting in all these bimodules, and there is this two-term complex, and there's a map from here to here. There's a map from here to here. And I think that's all what I want to say. And this is like, before it was 1 minus q times just q minus q inverse times 1. And this is like what this becomes. Anyway, don't want to say too much. I want to mention two facts. One fact and one open question. So theorem of Lebedinsky-Williamson says that TW for W and Sn form a semi-orthogonal decomposition of my categories, so either SB-man or affine SB-man. So what does it mean? It means that this, so before, if you remember, we had a statement that TW is the basis of the Hecke algebra. Here we're saying it's not the basis, but every element of this Soergel category you can resolve by some complex of TWs. And you have home from TV to TW is equal to 0 unless V is less than W in Bria order. And this is really powerful tool, and this is kind of categorification of the statements that TW form a basis of Hecke algebra. This maybe I'll write it explicitly. So this categorifies the fact
So this is somehow algebra.
that TW form Yep. So TW is a complex, and you can resolve everything as a complex. So, but like any Soergel model will be resolved by these complexes. Any complex Soergel models will be resolved by these guys. And yeah, so this is kind of very much related to the picture that Katerina was explaining. That like for her, that corresponded to standard module labeled by W, to like Verma module labeled by W. And this home is related to like infinite situation, of course. And then this home is related to some kind of X between Verma modules, which was also ordered according to this order. So the statement is that, yeah, so home to infinite. So home from CV to W is more or less the same thing as X from delta V, delta W in categorical. And so these are ordered like this, and these are also ordered like this. And there is some slight discrepancy for some technical reasons, but you can say like how to fix it. So yeah, this is just language to deal with this. And so this gives you like highest way structure. People see things like this, or semi-orthogonal decomposition. So the category is structured, but somehow TW is a complex, and we have to deal with that. Okay.
You certainly understand why the experiment is written on the right hand side. I understand the structure on the right.
And again, somehow, if you like people doing kind of more geometric representation theory than this, they would say that kind of TW, they correspond to some like infinite situation. There will be some kind of reverse sheaves and flag varieties. And then you can study these homes or X between them. But in a affine situation, again, suddenly everything is complicated because you have affine permutations and affine flag varieties and reverse sheaves and affine flags. And that's hard. But like here, it's like really the same proof works, and everything kind of works the same way. All right. Do I want to say more? I want to say one more thing. So what we don't know, if I forget about geometry, yes, we just do formally with Soergel bimodules. And kind of I want to say this open question. Yeah.
You have it for the as a tilde, you have an infinite
Yeah. So any Soergel bimodules has a finite resolution by this TWs. So you need only finite many of them. Yeah.
Is that like
In what sense? I mean, it's just like any Soergel bimodule you can resolve by finitely many of these TWs. Because you can like order them according to lengths, and like there are finitely many things of smaller lengths. But yeah. Okay, open question. So we don't know, and it would be a great question. So how to categorify?
The affine versus the Categorical.
Yeah, because like you guys have this affine algebras and things. So I mean, probably that's all related. So I don't know. So the question which I don't know, which is like very delicate and related to Katerina-Stokes directly, is how to categorify these things. And maybe. And again, the problem was precisely the same as what she was explaining, that somehow we need to know how to multiply things. We need to know how to multiply morphisms, how to slide things kind of in the middle cylinder through the other one. And this would be true up to homotopy, and how to control all this higher top homotopy. So this would be necessarily some kind of A infinity functors from affine Soergel bimodules to affine Soergel bimodules. But this is not constructed, but maybe actually this recent work of Katerina and Bedrich and other people, this would help, I'm sure. But this is not done. So somehow, by the same reason that kind of, you cannot just say that like if you have, like what she was saying is that you have some braid on this strands and some braid on this strands, then you can kind of slide things through in different directions. And they commute with each other naturally. But somehow here it's kind of the same flavor, but now like wrapped around cylinders and things like this. So this is very much the same flavor, not done, but maybe they've done enough actually work to do this. Okay. All right. So now we understand, at least in some way, what is the decodified story. We understand, said some words like how to codify this Hecke algebras now. What is the trace? And so this is, I also want to kind of black box the trace, unless you want me to say some things, but we'll see. So this is, what is a categorified trace? For cosenter. So let's do it completely abstractly. So C is some tensor category. And then, so there is a construction. So I want to produce some other category. This is some category. We call it derived horizontal trace. And the construction I'm discussing is in my paper with Hogenkamp, Bedrich, from a few years ago. And what are the key properties? So again, I have some kind of tensor category, and you can think of this Soergel modules or whatever. So there is completely abstract categorical construction, how to get this trace thing. So what are the properties? So first of all, we have some DG functor from C to through C. So if I have some object here, I know how to compute its trace. So again, like the same pictures that we had before, that morally we just start from X and close it up. Then kind of some key properties. Whatever. So for example, here I have distinguished object 1 and goes to some distinguished object 1. And so the fact is that in the morphisms in the trace of C 1 is partial homology. And another fact, which is much more useful. So if T has duals, then tur xy is isomorphic to tur yx
Is respect to the model structure?
with respect to the monoidal structure. Yes. I mean, what do you mean?
Not the way that the hum direction. But with respect to-
It's more with respect to home directions than with monoidal structure in some sense. I mean, ask a question.
What I have with this category here, I know the objects are more.
Yeah,
Are you claiming that I know the objects are more than Tracy?
yeah. Do you want me to write them down?
Yeah.
Okay. Let's start with that. Okay, forget this. Fine. Okay. So the objects of my Tracy are the same as the object of C. Okay. So the objects are the same. I mean, but like instead of X, I would consider the object trace of X, right? And then what I'm really interested in is morphisms. So I need to understand how to compute morphisms from trace of X to trace of Y. Okay, so this is a big complex. And I write here from in the C, in the original category, from X tensor Z, Z tensor Y. And I sum over all possible objects Z. Here I would take form from X Z1 to Z2 Y, and form from Z2 Z1, and so on. And here is again direct sum over Z1 Z2. Okay, and so on. So there is kind of infinite complex built out of these things. And so what's the differential here? So if I have some f in form from X Z1 Z2 Y, and I have my G in form from Z2 to Z1, then I can compose them in two different ways. And get Z1Y. Or I can compose them like this. And get XZ1, Z2Y. And I take the difference. So the difference differential of F tensor G would be whatever G tensor identity. Composed with F minus F composed with identity. G. Okay, so if you see, I don't know what's called homology category. I don't know. I mean, I know this. I don't know that. So somehow the point is that so here, like the tensor product appears exactly in one place, here and here. And so then we'll have like a lot of forms different. But like, yeah, I mean, if you know this infinity categorical stuff, like probably it's related. It is kind of bar complex with X and Y on two sides. So we have a bar complex, but we insert the X on one side, we insert Y on the other side, and then we kind of, and a bunch of stuff here. Yeah, exactly. But yeah, so, but in some sense, like the bar complex is with respect to homes, not with respect to tensor structure. And then we kind of squish in X and Y on two sides in the end. That's right. So yeah, if you know this probably better than I do, then yeah, that's what it is. But this is abstract definition. If you've seen bar complexes of categories and homology, yeah, if like if you see it for the first time, it looks insane because you take direct sum over all possible objects in a category and direct sum over like pairs of objects. But like the whole point is that this is computable, and I will try to explain how. Okay. Everyone's fine? Okay, so now let me write it again. Let's see what we know about this thing. All right, so what are the properties now? Properties like are the following. So we have a DG functor from C to true of C. So if I have an object, I send it to the object with the same name, true of X. And then if I have a morphism, I of course get a morphism there for like Z is equal to identity. So that's fine. And then kind of the key property. Okay, so the key property is that if C has duals, then tur of xy is isomorphic to tur of yx naturally in x and y. In some kind of infinity sense that, so what was the cosenter? Where did we start from? We're saying, so we want to kind of close up x and close up different things in the original algebra. And then we want to impose the relation that xy is equal to yx. This is categorification of that. So this is categorification of just a relation that xy is equal to yx. Now we're saying, so there's an object which is the closure of xy. There's another object which is closure of yx. There are isomorphic in the trace, and this isomorphism is natural in x and y up to homotopy, and then this higher homotopy is captured by this whole nonsense guy. Okay, and so, and I mean, in some sense, like if you know this and you know that C has duals, you can like reconstruct that thing more or less. And another thing which is good to know, like which is related to all these questions, is that so we have specific object identity in the original category. It goes to trace of identity in the trace category, and then in the morphism in the trace category, the trace of identity is actually functional homology of the original category. And that's really from that definition. So if I plug in x is equal to y is equal to identity, I get a big complex with all these z's, and that complex computes what is known as functional homology of the original category. So it's, I mean, yeah. And kind of maybe as a warning, maybe let me not say this warning, whatever. There are some technical things, you know. Okay, so now let's compute. So in finite type A, everything is perfect. So the first theorem from that paper is mad. So in finite type A, first of all, my trace is generated by the semantics of true of 1. Okay. Or by these derived rates, which were these things. So these are equivalent. These are two different generating sets, and you can express this in terms of this and this in terms of this. And then to describe this, so this is kind of first thing. the second thing is we need to know what is in the morphism of 1. And by that property, this is the same as Soergel homology of SBM. And these are just polynomials at x1 for xn, theta 1, theta n, semi-directives. All right. So if you see this, like you don't like Soergel homology, like what does it actually mean? So what is true of 1? So you take identity braid, you close it up, and then you're saying, so this is true of 1 for me. This is really what it is. Nothing more, nothing less. Now this collection of circles has this action of axis, thetas, and Sn. What is this action? So Sn just permutes the circles. So this is like n circles, and Sn permutes these circles. And then axis, you can put a dot in every circle, and this is like the same action of axis you usually have for link homology. So xi are kind of, let's say, action of homology of unknot, whatever, or unlinked. So I can imagine that, like, if I put the mark point here, and I draw a small knot kind of locally here, not wrapping around this whole thing, I can merge them together. And this will give me an action of unknot, homology of unknot on the homology of the whole thing. And this will give me xi. That's kind of one way to say this, maybe not perfect. And then theta is some kind of monodromy of this xi in some precise sense. Oops. Whatever. Okay, so
when C has duals,
so every object has a dual. It's like rigid monodal category. Left and right dual with respect to tensor product. And in this case, left and, like for S-beam, left and right duals are actually the same, so it's easier.
What I don't have.
If you don't have, like, you need to be careful. But like, in all our situations, we do so for fun. I'll draw a picture, and then I'll answer the question. So how does it actually work? Like, I'm interested again in this categorical skein of the animals in this case. And like, we want to compute things. So we're like, it's great. We have all these homology definitions and whatever. How do we actually compute things? So here's an example. So suppose that I want to compute something like this. Okay, so first of all, I have two circles. N is equal to 2, and we work in the trace of S-beam 2. Okay, so this is the trace of identity. And it has an action of S2, which swaps these two circles. Okay, so from that theorem, what does it mean? It means that in particular, I can define an object which would be called S2 here. And I can define an object which would be called wedge 2 here. And so if I take the direct sum, this will be precisely this. Okay, because I can kind of project to this amount and this amount. So the technical issue is that these guys are not in the trace. You need to idempotent complete the trace, but whatever. But this is fine. So you have some object which you can call S2, with some object which you can call wedge 2. Now let's compute something more complicated. So let's start with this guy. So that's a Soergel bimodule.
Are you saying that it's for these things they categorifies and I can kind of,
Yeah, in some sense. I mean, they only live in categorical land in some sense. Like,
I'm asking
Yeah. Decategorify that could correspond to like H2 and E2 in this in the solid torus. That's right. So they correspond to exactly to like H2, E2 in my skein of the solid torus. That's right. But somehow this analogy with symmetric functions, it was kind of formal in some sense in this. Yeah, but like I mean here it's very explicit because you're just saying that, yeah, I mean probably it's related to what you're saying, but like here I'm just saying, so I have this two circles, I can swap them and like I can formally define, so there is like the sum and when I kind of take 1 plus s over 2 and 1 minus s over 2, and this will give me this and this. Okay, so let's do something like this. So this would be the trace of bi, really.
So if we actually were doing an echelon, right, the answer would have been the corresponding short function. All the one.
Yeah, I think so.
Got some kind of course, it's isn't echelon, so.
Yeah, I think so. But like here we have all of them. That's right. Yeah. But it's still kind of true functions. Yeah.
Question. So back there in the theorem, this circle by module of n strands monoidal category?
Soergel bimodals, yes, of course. Soergel bimodals is always monoidal category. Because I can, these are like, you can tensor them over R. And this corresponds to stack and brace on top of each other. But the trace is not a monoidal category, but the trace, yeah, is what it is. Yeah. So the whole point is that like Soergel bimodals categorify Hecke algebra. So it was an algebra and we want monoidal category. Affine Soergel bimodals categorify affine Hecke algebra. So again, it's monoidal. But once we take a trace, we'll lose the monoidal structure. Okay, so I want to compute this. And so I want to compute this in a funny way that some of you may have seen. So I have straight it around. And I have this 1 and 1 here. And then I have a bubble. And so I can just say that this is 1 plus q times this thing. And then this thing is actually just wedge 2. Okay, so there is an object called wedge 2, which is really the same thing as just the circle colored with 2, if you know. I mean, you know this. And then there are 2 copies. So the claim is that this is now this categorifies. So there will be direct sum of 2 copies of this guy shifted by q. And now what is the crossing? So let's talk about the crossing. So this is by definition single crossing. Before you can write like this. Okay, so this is kind of, this is my T1 in this case, this is my B1, this is my identity. And now I'm saying, aha, so this guy, we know what it is. So this is 1 plus Q H2. And this is mapped to identity, which I can write as S2 plus H2. Plus whatever. And there is some differential here, which you need to compute. It's not obvious. And then if you simplify, then you simplify to something like just QH2 goes to S2. And so in this case, like this direct sum of 2 H2s, like one of them will cancel with this one and so this complex is really homogeneous to this one. And you can write the differential explicitly, and this will be some kind of x1 minus x2. And so in this sense, I can draw some braid and I can resolve this thing by just these symmetric functions, which will be summands of a trace of identity. And so that's kind of the meaning of that theorem. And we have lots of these computations in that paper and a separate paper with Paul, where like we show how to actually compute things explicitly with this. So it's not just some functional homology computation. It's actually some very direct computation and direct categorification of derived. Okay. All right. So now what happens in affine? So finally we get to affine. And that's interesting. And if you know some geometric wrap theories. So this trace of Soergel bimodules is supposed to be related to character shifts. And so in type A, character shifts are generated by some answer of the Springer shift, and true of 1 is like the Springer shift here. But if you don't care, that's fine. Like you can just think about braze and draw this picture.
So maybe
Good for me.
notation. The circle is a 2 marked on that. That means what?
It's like a colored, so it's a circle colored with 2. I don't know.
2 is like for the second term, the wedge 2, or
Well, for the wedge 2, yeah. So this is equal to this. Yeah, that is equal to this. Yeah. Whatever. If okay. So let me see now what happens in a affine situation. So this is the theorem. So in a affine type A, you can try the same computation. So the number 2 is still fine. Start with number 2. So now partial homology affine is equal to now polynomials x1, xn, theta 1, theta n. I mean, there is some subtlety, but let me not talk about this. But kind of the most interesting thing is this. So you have a affine Sn showing up in this. And so this is the same thing as the endomorphism 0 of 1. And the number 1 and the trace of affine as Bman is generated by, let's say, the cement of P and 1 and 1 MK and K, where again, let's say M1 over N1 and now what are these P's? They're defined exactly the same way as before. So somehow the whole point of this building this machine is to say that PMN is still the same thing with the trace of omega to the M, T1 to TD minus 1, or D is GCD of Mn. So I'm saying, okay, so these are some complexes of Soergel bimodules. Omega is some Soergel bimodule. Tensor them all together. That's some object in my category ASBMN. And then just take the trace and call it now PMN. That is the well-defined object in the trace. Now, there is an issue with the star product because I say it's not defined. So you need to kind of carefully define what this even means, but that's possible. Let me skip that. But the point is that, yeah, so the kind of non-trivial fact is that, first of all, it's not generated by some kind of T of 1. And like we saw this, there are lots of different things with different convex paths. And here we reproduce the same thing here. We're saying, so actually different convex paths give us very different things. And so we have all these things, and conjecturally, they're all independent in the category. We don't know that yet. And kind of one thing which we can prove is this endomorphism of, say, PMN. So if they're all on the same line, if GCD of Mn is equal to 1, and if they're all on the same line, then the endomorphism of this thing is actually again polynomials in x1 for z, theta 1 theta t. semi-direct product with the finest. So we can compute some things, and so in particular we can say, so if I have a product of, so you can think of this as like d copies of a man torus knot stacked on top of each other, and then we can, so there is affine SD action which flips them around. So this is d copies. Huh? Question? No? The X is commute, theta is anti-commute, X is commute. This is like even this out. So this is like commutative, but like I said, tilde would permute them in an interesting way. Yeah, and so somehow all the different, like you don't see them in the objects. Like on the level of objects, you basically see this action. I mean, again, you don't see just this action because it's not generated by theory of identity. But like here, for example, like this S2 and H2 to define them, you just need to know that there is a S2 action. But on differentials, you see them showing up because like there is some axis here, there is some axis here, and the differential actually depends on axis and on theta sometimes. And we can compute examples where differential depends on all this. All right, so this is getting too abstract. Yeah, I mean the supercommute, like, so these are like in degree 1, this is in degree 0 in some sense, yeah. Yeah.
Can you say a little bit more about how you could define the stuff product and
I mean, this will be just trace of some more complicated thing. Well, let me actually say this, because that's important. So, okay, let me say this way, so more general now. Objects. Third, y1 d1, yk dk, y and dn. Then you have t. Here I can skip t and 1. So I can begin. So in total, I can take this derived braid, which is just a subword of t1 to tn minus 1. Skip some letters. So I'm saying I'm going from here to here, then I skip one, then I go from somewhere to somewhere, skip one, and keep going. And then here I can put any product of y's. And so then the claim is that, so first of all, this also so this also generate sure. And this is kind of an important step. And then all those things you can get from here by specific choice of these. Let me just say this. So for some choice of this, we recover this one. So the point is that like this is some explicit braid. It's not like some complicated complex. It's like actually some braid, and this is some braid. Like we put this braid inside this braid, and we want to braid like the total braid explicitly, and like this can be done like this. And like all these issues with the product is more like what happens to the morphisms, what happens to kind of longer complexes. But like these are braids. I know how to stack braids inside each other.
Oh, no, category.
Yeah, that's right. But like on the level of objects, like in for braids, we know what to do. It's like for like morphisms or like complexes or twisted complexes or braids, we don't know. But like this is fine. Right. So this is cool. So now why do we care? So last 15 minutes. So we can say more about this affine situation and like why did we got interested in this? So conjecture is that the trace of, let me put it this way. So this is related to Mina's questions before. So how it's related to the Hilbert scheme? So the conjecture is the trace of finite SB is related up to some subtleties which I'm not going to explain to the derived category of coherent sheaves on the Hilbert scheme of endpoints on C2. And the trace fine has been met. Is the derived category of coherent sheaves on the commuting stack. Using the commuting stack. And we have two matrices, X and Y. The commutator is 0. And I think Y is important in this setting, at least. Otherwise, there are some issues. Portion by GLM. And so there is such a thing. It's like pretty complicated commuting stack. There is much better behaved Hilbert scheme of endpoints on C2. And so the conjecture is that the trace category for SBMN is actually the same as the derived category on Hilbert scheme. So this was the conjecture of myself, Andrei Negut, and Jake Rasmussen. And this is kind of a fine upgrade of this conjecture. So this. And there is some related work of Nadler, Lee, and Yoon, especially related to this one, which is slightly different. And we'd love to know how it's related. And like their stuff is not graded, whatever. But because that's where we can compute things, right? So this is kind of also so related work. Since I'm being recorded, let me say this very clearly. By Lee, Nadler, Yoon. And this is, in some form, this is myself, Negut, and Rasmussen. And I mean, there is also related work by Blanko-Rosansky, of course. And many other people. I mean, because, okay, so this one I can explain. The affine case, I mean, again, because there's a finite complexes, like if we take in like incompletion of everything, that maybe it's true, but like we want much stronger statement that's kind of actual like complexes here. So like, yeah, so if you want incompletion here, you need incompletion here. Okay. I'm not sure. Huh? Oh, yeah, we have evidence for this conjecture. And so like one evidence, so let me put this is ASB. And so kind of for A, we now have like tons of evidence, and maybe like, okay, depending who we talk to, maybe it's like almost proven or proven, whatever, but like kind of one, in this context, the biggest evidence for A is that, so we know that we have this Procesi bundle on Cuban of C2, and it generates, and this is a theorem of Bridgeland-King-Reed, that the derived category of coherent sheaves on Hilbert scheme is the category of modules of endomorphism of Procesi. And endomorphism of Procesi, just polynomials, and x1 through xn, y1 through yn. Same directs. Okay, And this is like, it generates, it's nice tilting bundle, there are no higher self-x, and we have lots of nice properties. And they should be compared to the theorem, which I unfortunately erased. So this is compare.
Where X and Y coordinates.
Yeah, x's and y's are coordinates in C2, exactly. And so we have the trace of S beam is generated. So that Sn permutes these x's and y's. If you like, it doesn't commute with them, but it permutes them. No, you don't keep symmetric thing, but if I have xi times permutation, they commute, but like x, yeah. So this is generated by again Tur of 1. And then in the morphism of Tur of 1, I'm just rewriting what was here before. So this is these polynomials on x1 through xn, theta 1, theta n slash sn. And so this is very similar to this, except you trade your y's for odd variables, and there is some kind of causal duality going on. And there are some other technical issues, but like mod this is very similar to this. So you can name in particular, like Tur of 1 should go under this pointer to just purchase it in some sense, and then everything matches up to this causal duality. Okay, and then somehow the problem is that, so this is cool, but there is nothing like this for the commuting stack, because commuting stack has like lots of different objects. And here we know that it actually is not generated by Tur of 1, so what to do? And so in case B, we have these guys, and like we actually know explicitly, so the conjecture.
Because again, replacing the equation of I1 with C2 by C times star.
This thing? No. But the odd variables, no, it's more like, again, when y is important, you have to kind of dualize in the y direction. Maybe, I don't know. I'm not sure. But somehow in the second case, so let me finish this. So we have these guys, and what do they correspond to? So the trace of whatever, y1, yn dn times tw. So they should correspond to the following thing. So this is certain explicit objects. Derived category commuting stack. Constructed by Negut. And his student Eugene. And what are these objects? So I have flag commuting stack. Let me just say, not explain things because that's too much. You have a map to commuting stack. And here I have some line bundle. And you have just a forward of this line bundle. So this is push forward. No. Line bundle. And so we actually know exactly like what these things are supposed to correspond to on the commuting stack. And I think this is different from, I mean, it's kind of very related to this approach. I don't know how it's related to this approach because they work like very categorically. They don't care, in my understanding, that much like what happens to individual objects in this. And like we have like, I want to name some object here and say where it goes to here. That guy, and that was the main goal for us. And somehow here we're saying, okay, so here is like explicit braid, very long, very complicated, but like understandable in principle. I can draw this braid. And so this braid gives me some complex of affine Soergel bimodule. I can close it up, get an object in the trace. And then what do I get here? This is some explicit object here. And then you can ask, okay, so you can test this conjecture in many different ways because you can say, for example, here, you have lots of interesting morphisms between these guys, which were constructed by Andrei, Eugene, many other people. And then we can check if there are morphisms on this side, and we see them, and that's very, it gives you some interesting relations in the paper. And also kind of one motivation, which I want to finish with, is the theorem of Negut.
Sorry, that's the Why is your commuting stack? Should I think of them as X and Y of C2 or not?
Kind of, yeah. I mean, you have just eigenvalues of X and Y in this. So you can think of Hilbert scheme as two commuting matrices and the vector in stability condition. So here you ignore the vector, you ignore stability condition. You still have two commuting matrices. So X's and Y's are like just the eigenvalues of X and Y. Okay, so let me just state one last theorem. So this is the theorem of Andrei. Is that if I take C star cross C star current of this commuting stack, so I take C star cross C star current K tier of commuting stack with this nilpotence condition here. So this is actually integral form of the elliptic whole algebra. And as I'm not explaining what this is, but we have explicit generators and relations. And so kind of one of the goals of this project is to say that, yeah, you have the generators and relations, you can leave them naturally to derived category. That's not hard. We know how to leave like most of relations. We don't know all of them maybe, but like most of them we know how to leave to derived category. And then you can say, okay, can we go to the left-hand side to these braids and affine Soergel bimodules and find these generators? Yes, here they are, more or less. And then can we find these relations? We found some of them again in like some work in progress there. And then kind of, yeah. And so here we have two parameters which scale X and Y metrics, which are Q and T. There we kind of not obviously have T, we just have one parameter from the grading, and we have homological grading, but it's different from this T. And so that's related to lots of other questions which we like. But maybe I don't want to say this. And maybe one last thing is that I don't know.
Maybe the
Okay, and like, I mean, maybe one last thing which kind of relating this to conjectures is that you have this action. Oh yeah, so you have like also kind of, there's a part of this conjecture, maybe kind of part C. So you have this AHM, or like whatever. We want to kind of categorify this product, which I mentioned. So this would be some kind of ASB man, ASB M, with ASB n plus n. Like to some extent, we understand on the level of objects and all these problems, but then what does it correspond to on that side? On that side, we have perfect understanding because we have this correspondence between commuting n cross commuting m and commuting m plus n. And we have some explicit correspondence between them, which is well known how to build some convolution product on this and this to this. So there is some kind of convolution product on these derived categories of commuting stacks. And this should be compatible with all the structure that we have here. And the same way, we have this action of HN cross HM, HM plus n. And again, this should give me some action of commuting stack n cross Hilb m to Hilb. I mean, again, do some kind of correspondence to Hilb m plus n. And then this is also well known because you can think of the derived category of commuting stack as some correspondence between this and this in some sense. And you can act on the Hilbert scheme and get another Hilbert scheme. And so all these product structures, if defined correctly with all these like subtle infinity corrections, they should give you this. And kind of one motivation for Andrei and I is that like this theorem in particular implies that the elliptical algebra acts on from the Hilbert scheme to the different Hilbert scheme. And this is this action. And this is, of course, the same action that, for example, Min and Shamil used in construction of refined link invariants. And so this is all kind of very much related. Yeah. I'll stop here.
Perfect.
Yeah.